Hey, welcome to 12.5, Probabilities of Independent and Dependent Events. So what we learned in section 12.4 was when you have a single dice draw or a single card draw and I want more than one thing to happen. But what we're doing today is when I have more than one card draw or more than one dice draw, when I'm doing multiple things. So I have multiple events going on, and when I have multiple events going on, I'm actually going to multiply my probabilities. Here's what I mean. If I have something called an independent event, that means that one event has no effect on the other. Here's what I'll say. The occurrence of one event has no effect on the other. So for example, if I flip a coin and I flip a coin again, the first coin flip has no effect on the outcome of the second coin flip. Here's how I say this in our formula format. The probability of A and B is the probability of A times the probability of B. So I multiply them together. Now something is considered a dependent event if the occurrence of one event does have an effect on the other. Has with one S. There we go. The occurrence of one event has an effect on the other. And this one has a fancy thing to it, so listen closely. Again, I've got the probability of A and B, and that is equal to the probability of A times the probability of, and we write it B vertical slash bar A. But what that means is the probability of B such that A already occurred. Sometimes I recommend to students that they don't necessarily use the formula as much for this type of problem, the dependent and independent event ones, because normally students don't have as much trouble with these. The OR problems are the ones that people struggle with usually. I'll show you what I mean in a little bit. When I start off here, I am going to write everything out. Let's look at example 1A. A jar contains 12 red, 16 blue, and 18 white marbles. 3 marbles are chosen from the jar with replacement. What is the probability that none are white? Okay, with replacement, you need to know this. What that means is they put it back before picking the second marble. So they picked up a marble, put it back before picking up the second marble. That makes the events independent because every time you start a marble draw, you have the same amount of marbles in the jar. So again, with replacement means they put it back before the next draw or the next event. All right, so I am drawing 3 marbles. So what I want is I want not a white marble times the probability of not a white marble times the probability of not a white marble. And you will see our probabilities today are going to be a lot smaller because whenever you want more than one thing to happen, the probability decreases because it's not as likely. If I count them all up, just the red and the blue, because those are the not white ones, there's 28 and there's 46 marbles in the jar total. So 28 out of 46 are not white. And again, I picked a marble, but I put it back. So 28 out of 46 on the second draw, 28 out of 46 on the third draw. And for these, again, we'll normally have small numbers, and normally they would be really strange fractions if you tried to leave it in fraction form. So the probabilities today we're going to usually put in decimal format and give me 3 digits. Sometimes I might do more or less depending on how many zeros are in there and if it rounds nicely or not. So that one, my probability is 0.226. All right, part B, we got the same jar, But now I want 2 marbles are chosen from the jar with replacement again, so I put them back. I want the probability that you choose a red and then a blue marble. All right, so first I want the probability of red, and then on my second draw I want the probability of blue, and I multiply them together. So I got 12 out of 46 for my reds, 16 out of 46 for my blues. Multiply those together and you get 0.091. And note, if you're someone who loves using your calculator, I recommend that you just put the fractions in parentheses to make sure that you get the correct answer. Part C, find the probability of drawing an ace, then a face card, and then a diamond from a standard deck of playing cards with replacement. So again, all of these so far have been independent events because we've replaced the card or the marble before picking the next one. All right, so I want an ace, and then I'm looking for a face card, and then I'm looking for a diamond. Remember, standard deck of cards, 52. So there's 4 aces, 12 face cards, 13 diamonds. And again, these are all separate draws. So I'm not subtracting off anything here because they're separate card draws. When I type that in, I end up with 0.0044 for my answer. Part D, during the 1997 baseball season, the Florida Marlins won 5 out of 7 home games and 3 out of 7 away games against the San Francisco Giants. And then during the 1997 NL Division Series with the Giants, the Marlins played the first 2 games at home and the third away. They won all 3 games. Our question is, what is the probability of that happening? Okay, so sometimes you have to think outside the box a little bit with these. So remember, they've got 2 games at home, the third game is away. I want to win all of them. So the first thing I want to have happen is I want to win at home. But it said there's 2 games at home, so I want to win at home again for the second game. And then the third game is an away game. I still want to win, but it's away. And if I look at the information they gave me, they actually told me these probabilities. It says they won 5 out of 7 home games against this team. So we got 5 out of 7 home is their probability of winning at home. They won 3 out of 7 away games. So 3 out of 7 for the away. And when I multiply that together, I get 0.219. I hope that you're writing down questions or making notes when you're not quite sure about what I'm doing. I'd love to go over a few of these again in class if we need to. All right, let's keep going. I'm just going to give you several more examples, and I hope that every example we do and we'll make it clearer. But again, one thing that's kind of difficult about probability is that every single question is slightly different. So it's not like you can memorize how to do a problem. You have to kind of understand the concept here of us multiplying together the probabilities. All right, now for part E, I want to find the probability of rolling doubles and then rolling doubles again when rolling 2 dice. So probability of doubles times probability of doubles. And at this stage, you might not be writing down in words anymore. That's okay. Once you get the hang of these ones with the multiplying, you don't have to write down the words. It's not required. I know that there's 6 ways I could get doubles out of the 36 options for rolling my 2 dice if I look at that little dice sheet I gave you. So that would be 1 out of 6. And assume that your dice rolls are independent. So I get 1 out of 36, or 0.028. Part F, 2 integers 0 through 9 are chosen by a random number generator on a computer. Ooh, what's the probability of choosing the number 2 both times? Okay, so I want the probability of getting a number 2. Assume they're equally likely, so there's 1, 2 in the batch. Second time I draw, there's still 1, 2 in the batch. So 0.01 is my probability for that. Part G, you are tossing a coin 5 times. What is the probability that the coin lands heads up all 5 times? All right, so actually there's a 1/2 chance of you getting heads. So every single time you have a 1/2 probability of getting heads. So if I'm going to flip my coin 5 times, here's what that looks like, which is 1 out of 32. For some reason, I didn't find the decimal for this one. Guess what? The probability of tossing 5 tails is also 1 out of 32. Part H. In a survey, 9 out of 11 men and 4 out of 11 women said they were satisfied with a product. If the next 3 customers are 2 women and 1 man, what is the probability they are all satisfied? Okay, so this one's a little more complicated, so I'm going to go back to writing out the words. So what I want is I want a woman that's happy with the product, and I want a second woman that's happy, and then I want a man that's happy. And they told me 4 out of 7 women were happy with the product. And then 9 out of 11 men were happy with the product. So you end up with approximately 0.267 when you multiply those together. Pause, go back and rewatch anything you need, and when you're done, flip to the back. Everything we've done so far has all been independent events where one thing did not affect the next thing. So for example, one coin flip does not change the outcome of the second coin flip. Or in the last example we just did, we could assume that one woman being happy with a product had no outcome or no effect on the second woman being happy with the product. Now we're going to talk about the dependent event side of things, which I gave you the formula for way at the beginning. Our first question is, a jar contains 12 red, 16 blue, and 18 white. 3 marbles are chosen without replacement. What is the probability that none are white? Okay, so this is actually, I made this the same exact problem as example 1A, only this time it's without replacement. So if I told you with replacement was putting it back, you probably can guess. Without replacement is you don't put the marble back before the second draw. Or you don't, without replacement, you don't put the card back that you've drawn, that kind of thing. All right, so I want the probability of not white. You know what, I'm not going to write this one out in words. I'll just talk about it. So check this out. Your first draw, you want not white. There are 46 marbles. 28 are not white. When we are doing probability, always assume you got what you wanted. So now I took 1 marble out of the pack. I know that it's either red or blue because I wanted not white. Assume you got what you wanted. So now there's only 27 marbles that are not white left in the jar, and there's only 45 marbles total left. Once I've taken out that marble, now there's only 26 not white marbles left in the jar, and there's only 44 marbles total. Go ahead and multiply that all together and see what you can get for your answer. While you're doing that, just again, always assume you got what you wanted when we're doing probability questions. That's the thing that kind of throws people off with these. All right, let's go to example B. You and 2 friends go to a restaurant and order a sandwich. The menu has 10 types of sandwiches. Each of you is equally likely to order any type. What is the probability each of you orders a different sandwich? So this problem is kind of tricky, so listen closely. You have 10 types of sandwiches to pick from. So when you order, there are 10 choices out of 10. Now we want your friends and you to pick different sandwiches. So there's still 10 sandwiches on the menu, but in order for you guys to have all different food, your friend only has 9 options to pick from because you already got one of them. And it said there is 2 friends with you, so the third person, there's still 10 things on the menu, but now 2 things have already been chosen, so there's only 8 left for that person to think about. And your probability ends up being 0.72 for that one. Part C is similar to Part B. I made a similar question because this one's always kind of hard. So now I've got 3 kids. They have 12 summer camps to pick from. Every kid's making a random choice. I want to know, what is the probability the 3 kids all attend different camps? All right, so there's 12 camps to choose from. The very first kid could pick all 12 of them. That's fine. There's still 12 to pick from, but now we want the second kid to only pick 11 of them because we want it to be different than the first kid. And the third kid only has 10 to pick from because 2 have already been chosen. So this one ends up being 0.76 for my probability. All right, look at part D. The probability of selecting a rotten apple from a basket is 12%. What is the probability of selecting 3 good apples? So if you know the rotten is 12%, remember what I want is going to be 1 subtract 12%. So you got an 88% chance of getting a good apple. And they're all different baskets. So if I've picked one, I go to the new basket, I've got the same probability. So 0.88 3 times. So this one I put under the dependent section, but I guess actually it's independent. All right. We haven't talked very much about the without replacement thing. So with example 3, we're going to go back to decks of cards, and we're going to talk more about without replacement. All right, number 1A, for example 3, find the probability of drawing a face, then an ace from a standard deck of cards, first with replacement. So that means, again, I put it back. So 12 face cards, 4 ace cards. So I end up with 0.018 when I round it. Now that's with replacement, so it got put back. So without replacement is, assume that I chose a face card out of the deck, so there's only 51 cards left now, because I didn't put it back before my second draw. But there's actually still 4 aces, because I didn't pull an ace out, I drew a face card. So that one, when I multiply that together, now here's one thing that's kind of interesting. So if you round it, it ends up being the same, but if you look at the actual decimals out to a few more decimal places, you will see that they weren't actually that similar. As similar anyways. Okay, the second one, what's the probability of drawing a 2 and then a 10 from a standard deck of cards? So with replacement, there are 4 2s in the deck, there are 4 10s in the deck. I'll round out to more decimal places this time. Then without replacement, there's 4 2s in the deck. There are now only 51 cards left, but there are 4 10s still, because I didn't pull a 10 out. And again, very similar to 2A. Number 3. Find the probability of drawing a king and then another king and then a third king from a standard deck of cards. Okay, so first with replacement. So I want 3 kings. I put it back in between every draw. So every single time, 4 out of 52 is my probability. Here's my probability. Very small probability of drawing a king and then another king when you put it back. All right, but even smaller probability is now without replacement. So now there's 4 kings in the deck. On my second draw, there's only 51 cards left, and there's only 3 kings left. So assume I picked a king out, and on my third draw, there's only 2 kings left, and there's only 50 cards total. So 0.00018 for that one. Wow. Very small probability. Last but not least, example 4. You will be required to read charts and tables to find probabilities at times, and we will practice this more in class. But right now I've got a table showing the number of endangered and threatened animal species in the U.S. So first of all, I want to find the probability that a listed animal is a reptile. So out of all the animals, everybody listed there, what's the probability of getting a reptile? By the way, I added these up for us earlier, so you do not have to. There are 475 total animals in this chart. And if I look at the reptiles column, there's 35. 35 of them are reptiles. So 35 out of 475, and I end up with 0.074. Okay, now here's where it gets a little tricky. I want to find the probability that an endangered animal is a reptile. So what they're telling you is we are only looking at the endangered animals, not any of the others, only the endangered, And I want to find what's the probability those guys are, one of them is a reptile that I select. Okay, so there's actually 14 reptiles that are endangered, and in the endangered only section, there's 355 animals. And I end up with 0.039. Now we're going to do more practice with that example 4 in class, but please make sure you write down any questions you have. Go back and rewatch anything you need to, and thanks for listening. Have a great night.